Okay. Now let us look into the idea of approximating using step functions. So I have some continuous signal and then I want to approximate this using some sequence of step functions like this. So you can fill this diagram throughout. Okay. Now our goal would be to approximate a smooth continuous function using step functions. Of course, you may even philosophically ponder about step function is a discontinuous function, and how would I want to approximate a smooth continuous function with discontinuous functions, right. I mean, this is a natural question one would get, and the answers to all of these have been thought about by folks working in analysis. I mean, this is a whole topic of study there. I mean, what is a measure of such discontinuities, etc., because you cannot have, if the measure is really finite, then it would be very hard. I mean, if you should have finite number of such discontinuities, right. I mean, you can't have many discontinuities, I mean, which is possibly if you have uncountably infinite discontinuities and you want to approximate the function, that would be hard. So, there are these subtle issues, but from an engineering perspective we will see how we would want to approximate a given function using wavelets or such step functions. Now, from the theorem that I stated, we can do successive decompositions of subspaces. So, what do I mean by this? So, we start with our equation Vj is Wj minus 1 direct sum with Pj minus 1, right. So, I keep Wj minus 1 the way it is. I now decompose Vj minus 1, that can be written as Wj minus 2 direct sum with Pj minus 2, and now you get a trend. If you continue this in a sequence, you have Wj minus 1 direct sum Wj minus 2 direct sum dot dot dot. Finally, you will land up with W0 and V0. So, what this means is each function f in Vj can be decomposed uniquely as a sum of functions which belong in the space Wj minus 1, Wj minus 2, so on and so forth, right. So, that is the meaning of this decomposition. So, any function f in Vj can be uniquely decomposed as a sum where f is, now these are signals, I just use some w like this, wj minus 1, this is not a space but a function, right. Plus f0. Now wl can take care of a short burst of width 1 upon 2 power L plus 1. I mean, this is the resolution. So, I initially mentioned if you were to do denoising or sort of remove these spikes or clean up the signal, then you have to identify to which scale you would want to do the wavelet decomposition, then I would figure out those spurious spikes and then just null them off, right. So, basically what you have is basically a control when you decompose the original signal into various components, each component residing in an appropriate scale with a resolution, right, and you can go to that appropriate space, and if you figure out that there is a spike there, you can just null that spike out, and this is an important application. Now, a more deeper result would be to ponder about if the space L2R can be decomposed into an infinite orthogonal direct sum space, right. If the space itself in L2 can be decomposed, and what is this this general result. So, let me state this as a theorem, and I will give you some ideas towards it. A formal proof of this theorem will require a background in analysis in math, and I will leave this as a sort of a study exercise, but it is not intended as part of this course. The space L2R can be decomposed into an infinite orthogonal direct sum space. So, what it means is L2R can be written as V sum V naught with W naught with W1 dot till infinity, which means some function f belonging to L2R can be written as f is some f naught plus limit n going to infinity summation j equals 0 to capital N Wj, where f0 belongs to V0 and the small wj belongs to the space Wj. So, I will tell you what is the difficulty in the proof of this result. So, there are two major points one needs to really establish. The first point is any function f belonging to L2 can be approximated by continuous functions. This is the first statement that needs to be proved. Then any continuous function can be approximated as desired by a step function whose discontinuities are multiples of 2 power minus I for large I. So, these are the two subtle aspects, because this summation is heading towards infinity, right. First is you have to establish that any function in L2 can be decomposed or can be approximated by a continuous function, and that continuous function can be approximated as desired. This is very important. That means you have some metric for the error tolerance that you have to account for in terms of some norm by a step function whose discontinuities are multiples of 2 power minus I for large I. So, I will leave this as sort of just to ponder upon. I mean, I do not expect it because it will require analysis, but I will provide you supplementary notes to the proof of this theorem just for your understanding, but it is not intended to be part of this particular course. If you did a detailed course in harmonic analysis, probably you will have to consider these aspects here. Okay. So, now with these ideas, we have to get into Haar decomposition. So, what is the intuition? So, going back to our motivation, where we wanted to isolate a short burst or spike from the theorem on subspace decomposition, right. We saw that Fj can be written as F naught plus some W naught plus W1 plus dot dot dot, right, and a component Wk belonged to space some W, capital Wk, with width 2 power minus k plus 1. So, for example, suppose we have a 5 millisecond spike, then we know that 2 power minus 7 is less than 0.005, is less than 2 power minus 8, and you can choose your scale appropriately to null out the spike, and the resolution in the smallest scale, right, I mean that you would consider in your decomposition would be roughly what your sampling has to be. Okay, these are important things. I think with this motivation in mind, we will start with the wavelet decomposition procedure. Okay. So, let us consider the wavelet decomposition process. So, this is best understood through an example first, and then we will formalize. So, before we begin, we would like to recall some relations that would be useful in our decomposition. Phi of 2t is basically psi of t plus phi of t upon 2. This is one important relation. That is, I want to realize a box car of width half, and that I can realize using adding the wavelet and the scaling function, right, in a resolution which is coarser than that. Now, phi of 2t minus 1 is phi of t minus psi of t upon 2. Call these two relationships A, right, equation A. And you must also recall that psi of t is phi of 2t minus phi of 2t minus 1, right. You translate it and you flip it, you get the wavelet. It is intuitive. So, now with this, let us start to understanding how the decomposition process works through an example. .5, 1, 1.5, 2, 0.5, 1, 1.5, 2. Here I have half, this is 1, this is 3/4, then there is 1.5, this is 2. T here, some f of t. So, until half this is basically 2, then there is a sharp dip, it comes to 1, then for the next quarter time step it maintains at 1, and then there is again a discontinuity here, this is 1 minus 1. It stays for the next 1/4 time duration. And basically returns to 0 and then stays at 0. Now, we may find such pulses. A good example is if you look into a waveform which is pulse width modulated that appears in your power systems, etc., you will see such staircase type of functions of various widths and so on and so forth. But our goal is to basically decompose this this signal. Now, if you look at what the smallest bin is, the first step we will call as observations. Smallest bin is of width 1/4 time steps. Time units, and we see this between 1/2 and 3/4 and between 3/4 and 1. This is a semi closed interval just to indicate that this is a point of discontinuity. Okay. So, now it is obvious that we can describe f of t over V2. The space we can consider is V2, f of t belongs to V2, right. We can describe f of t over V2, which means that we can express f of t in terms of these phi functions in over scale j equals 2, this is 2 square t minus L belonging to set of integers. That means I can expand f of t using this as my basis. Now, f of t can be written as 2 times phi of 4t plus 2 times phi of 4t minus 1 plus phi of 4t minus 2 minus phi 4t minus 3. Directly, if you observe the waveform, you can express this using this relationship. Now, let us do the wavelet decomposition. So, let us do a wavelet decomposition of f into spaces W1, W0 and V0. That means you will have a component in W1, a component in W0 and in V0. So, f belonging to V2 implies f in this space V2 can be written as f0 plus some component W0 and some component W1. Now, from our equations in A, we can generalize it for an arbitrary scale. Phi of 2 power j t is psi of 2 power j minus 1 t plus phi of 2 power j minus 1 t upon 2, and phi of 2 power j t minus 1, just a translate of this can be written as phi of 2 power j minus 1 t minus psi 2 power j minus 1 t this upon 2, right. This is a generalization. We could visualize it for V0 and V1. So, we can now extend it to arbitrary scale. This is a straightforward generalization. Now, what we do is we plug j equals to, because we have these terms, right, we have to get these terms, phi of t, phi of 4t minus 1, phi of 4t minus 2, 4t minus 3, we have to get all these things. To get to this step, we have to use these formulae and then decompose things further. Okay. So, let us see how this works out. Now, phi of 4t is basically psi 2t plus phi 2t upon 2, and phi of 4t minus 1 is phi of 2t minus psi of 2t upon 2. Now, how would I do phi of 4t minus 2? This is phi of 4 into t minus half. So, now this is basically psi of 2 into t minus half plus phi of 2 into t minus half this upon 2. Because once you realize what phi of t is, you can sketch what phi of t minus half is and so on, and then you can just get the rest. And similarly, you have phi of 4t minus 3 is basically phi of 4 into t minus half minus 1, and this you can write it as phi. Now, use the phi of 4t minus 1 formula, and then you can write it as 2 times t minus half minus psi of 2 into t minus half this upon 2. Now, we have expanded all these forms, and then we will try to group the terms. So, grouping the terms, f of t is basically psi 2t plus phi 2t plus phi 2t minus psi 2t plus psi 2t minus 1 plus phi 2t minus 1 upon 2 minus phi 2t minus 1 minus psi 2t minus 1 upon 2. Which is basically 2 times phi of 2t plus psi 2t minus 1. Now, this belongs to W1 and this belongs to V1. Decompose phi of 2t further. So, what we get is phi of 2t is basically phi of t plus psi of t upon 2. Now, we plug everything together, right, and then we land up with f of t is phi of t plus psi of t plus psi 2t minus 1. And if you see the spaces, this belongs to V0, this belongs to W0 and this belongs to W1. Let us write things explicitly, right? We write things explicitly. So, now phi of t, how does this function look? This is 1 for 0 less than or equal to t less than 1, 0 else. Now, this psi of t is 1 0 less than or equal to t less than half minus 1 between half and 1 and 2t minus 1. This is 1 from 1 half less than or equal to t less than 3/4 and minus 1 from 3/4 less than or equal to t less than 1, and I have to put a 0 else here just to be consistent. Okay, now you add all of these. Right, you take phi of t plus psi of t plus psi of 2t minus 1. So, what you get is this function. Now, phi of t plus psi of t plus psi 2t minus 1. If you add all these using these ranges, this is basically 2 from 0 to 1 half. It is 1 between 1 half and 3/4, minus 1 between 3/4 and 1, and it is 0 otherwise. So, we are basically home. We started off with this signal f of t, we decomposed it in the V2 space using the basis in V2, and then we looked at each of the components in V2, and then we further decomposed to a component in V0 and W0 and W1. Okay. So, this is the idea. So, V2 is decomposed to V1 and W1, and then V1 is further split into V0 and W0. and we did a 2 level decomposition. So, in your practical example you may need some D level decomposition, arbitrary level, because you know what application you want, you know to what level of resolution you want, right. You could go to that resolution, and that is where the scale is very important, and in that resolution you look at the scaling function, you look at the wavelet, and wavelet is basically the high frequency component here, if you can sort of imagine that in that way, and then you figure out what to null and what to retain depending upon what application you have in mind. Okay, so this clearly is a good example. So if you want to null out some signal in W0, you would just basically remove this component, right. If you wanted to null out something in W1, you would just null out some component here. So therefore you have full control over the decomposition part and the synthesis part to retain and null whichever components you need depending upon your applications. Okay. So now we have just got an example here. Now we will formally generalize this into an algorithm for wavelet decomposition, and we will derive the forward wavelet decomposition, and we will also look at the reconstruction part, and then we will try to link all of these to filter banks. Okay, we will stop our lecture here.